signal is too sensitive and the background is too huge, we just want to just optimize our selections. We invited a relatively new method. It's called boosted decision tree. Here I'm gonna give you some ideas about how it works. Here the boost decision tree is based on decision tree. We just add the boosting algorithm to it. The decision tree is basically a binary trees, and if you look at the right diagram, it's just separated from the root node. Select a criteria, separate to two sub-root nodes. One is contain signal in the background, the other is contain the signal background. Again, they separate to other one, and two, the leaves contain only signal or only background. That's basically how the binary tree works. And if you just apply this binary tree directly to our analysis, you will find it's not effective at all, because you'll foresee that it's pretty much similar to the straight cut. Sometimes it's even worse. So what we want to do is to do the boosting. The boosting here basically is the reweighting the events. Here, you know, it's every time you separate it, there's no such kind of a powerful classifier for you to finally separate the signal and the background completely. Every time you build a tree, some of the events will go to the wrong way. That means some of the events will be misclassified to signal, some of the background will some of the signal will misclassified to background, and some of the background will misclassified to signal. So what we do is want to increase these misclassified events, the weight of them. What we do is want to boosting their importance, because they are just not important. They are not that obvious. They are not that important. We want to boosting their importance to make them to go to the right way. So that's basically what I want to do. And in practice, we divided the data set to two samples. One is using as a training sample to build up the tree. The other is use the test sample to validate the tree. And here we input 22 variables for the input. Here the input variables are pretty much originated from the pre-selection criteria. It's energy, momentum, lepton isolation, event topology, and mass information. If you see the plots on the bottom, most of the variables, they are not that powerful. They're just weak classifiers. So the BDT want to do is combine these weak classifiers to a strong trees. And here is the BDT output. So let's first look at the bottom left plot. It's the red line is the signal, the blue line the background, the x-axis is the BDT output normalized to 1% of the bar. The y-axis is the events, number of events. Here the BDT output means the score, because every time an event landed on a signal or a background, if it landed on the signal, we assign +1 to the score, to that event. And if it landed on the background, we assign a -1. So that means the background will be on the positive score and the signal will get the the background will get the negative score and the signal will get a positive score. And if you look at the table, here shows you the BDT. If we cut on a specific BDT output, it will give us the number of signal we get, number of background we left, and the signal over background, and also the signal efficiencies. And if you look at the one row under the red line, it's about BDT over 200. The signal is about 152. The background is 16, and compared to our straight cuts, it's at least 3 times better. So BDT is very powerful. And if we want to use BDT, there's another things we have to do. We have to gain some confidence about it. It has to be stable. So we just selected 2 key plots The one is the transverse mass of ZW. We compare this BDT, the ZW signal distributions of the ZW mass of the signal distributions on the pre-selection, after the pre-selection, and after the BDT cut. If you look at the left top one, they are consistent with each other, very good. And on the right, you see after the mass energy of 170, the signal efficiency will hold at around 70%. So this is pretty stable. If you look at the bottom, the straight cut, you see the ZW mass, the peak, just located on the 170. So that means after 170, the BDT signal efficiency can give you a relatively stable one, and compared to the pre-selection and after the BDT selections, the distribution does not change. So that's what we want. And we also compared the PT of Z. Still, they are pretty stable. Alright, goes to the conclusion. What we do is WZ analysis. We use two methods. One is the Tetton street cuts. After that, we got a 53 signal and an 8 background. And also, we invited a BDT method, and the result is much better compared to the Tetton street cuts. And based on the selections, we calculate the WZ cross sections, and also analyze the statistical and systematic uncertainties. Finally, 19% precision for 4 decay channel combined together. The precision is 19%. Alright, thank you.